Welcome to this lecture series in linear algebra. In this lecture, we'll be talking about upper triangulable operators or endomorphisms, and we will see a criterion to decide when a given endomorphism is upper triangulable. Let us recall some relevant material. So we need to know the fundamental theorem of algebra. It says that if we have a non-constant polynomial px over the field of complex numbers, then it has a root. And as a corollary to this fact, one can show that px can be written as the product of degree 1 polynomials. All right. Another fact that we need is that if we have an endomorphism on a vector space V, and yes, everything is finite dimensional as always, and W is a T invariant subspace of V, then the minimal polynomial of the restriction of T on W and the minimal polynomial of the endomorphism induced on the quotient V mod W, we have discussed this several times, divide the minimal polynomial of T, and the minimal polynomial of T divides the product of these two polynomials. All right, so these are the problems, or rather there is only one problem just for practice. And now let us get started. So fix a field F and a positive integer n. Let M be an n cross n matrix over F. Then we say that M is upper triangular if all the entries below the diagonal, all the entries of M which are below the diagonal, below the R0. So I will explain that. So say M is equal to this matrix Aij. It's an n cross n matrix, and the ijth entry is Aij. So then M is upper triangular if Aij is 0 whenever I is less than j. So that's the proper way to write it. And let's see an example just so that there is no confusion. So let's say M is this matrix. 1, 2, 5, 0, whatever, 4, 3, 2, 1, 0. Let's make that 0. So we see this diagonal, and everything below the diagonal is these three entries. And these are all 0, and hence M is upper triangular. M is upper triangular. Let's say M were equal to 1, 2, 5, 0, 0, 0, 0, 1, 3. Then this is also upper triangular. There is an entry on the diagonal which is 0, but we don't care. We only need to talk about the entries below the diagonal. And if all of them are 0, then M is upper triangular. So this is also upper triangular. And I don't think there is any more need to get into any further examples. So we know what are upper triangular matrices. And here's the corresponding notion for operators or endomorphisms. So fix an endomorphism on a vector space V, and the base field is F, which I'm not writing. So we say that T is upper triangulable. There is no such thing as an upper triangular endomorphism. It's only upper triangulable endomorphisms. So we say that T is upper triangulable if there exists a basis B of V such that the matrix representation of T with respect to the basis B is upper triangular. So T is upper triangulable if there is a basis with respect to which T, the matrix of T, is upper triangular. Of course, this does not mean that every basis will have this property. If there is one basis with this property, then we declare that T is upper triangulable. Otherwise, if there is no such basis, then T is not upper triangulable. Okay, so I hope the definitions are clear. And here is another definition that we need before we state the main theorem. So fix a field F and a polynomial over F. Let's say, just for safety, Px is non-zero. So we say that Px splits over F. So maybe I should highlight everything. Splits over F if there exist field elements. I should write more neatly, A1 up to AN. So there exist these field elements, alpha and a list a1 up to an such that px is equal to alpha times x minus a1 dot 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 x minus an. So we are not insisting that these are distinct or anything. They could be the same. All of them could be equal. Right? So we say that px splits over f if one can find such scalars. This alpha is just there to take care of the leading term of px. If px were a monic polynomial, then this alpha would be 1. Right? So I hope the definition is clear. It's a fairly simple definition. And let's see some examples. So the polynomial, so let's say px is equal to x square minus 2. And this is polynomial over R. So then px splits over R because x square minus 2, and the reason is just that x square minus 2 is equal to x minus root 2 times x plus root 2. Okay, but importantly, let's say px is again x square minus 2, and you can think of it as a polynomial over R or Q. So let me think of it as a polynomial over Q. Doesn't matter. The point is, px does not split over over Q. So why is that? The point is, if it did split over Q, there would be a root of this polynomial in Q, which would mean that there is a rational number whose square is 2, which would mean that 2 is a rational, the square root of 2 is a rational number. So that's the reason. The reason this does not split over Q is that 2 is a rational number. Square root of 2 is an irrational number, forgive me. Right, so it matters over which field we are talking when we ask for splitting. Right? And lastly, one more example. Every non-constant polynomial over complex numbers splits over complex numbers. This is immediately by the fundamental theorem of algebra. All right. So here is the main theorem. It says that for any endomorphism on a finite dimensional vector space V over a base field F, so let's say base field F, T is upper triangulable if the minimal polynomial of T splits over F. A beautiful theorem. So one can detect upper triangulability just by knowing the minimal polynomial. And it's an if and only if condition. So it's a characterization. All right, so let's start proving it. There are two directions to the proof. So first we will do this direction, that upper triangulability implies that the minimal polynomial splits. So suppose not. So assume on the contrary that this is not the case. So there exists an endomorphism on some vector space V such that T is upper triangulable, but the minimal polynomial of T does not split over the base field F. There exists such a thing, and therefore we can choose such a pair, if you will. The pair is an endomorphism T and the vector space V. So we can choose a pair where the dimension of the vector space V is the smallest possible. So the statement that I want to write is, so let V be a vector space over F of smallest possible dimension such that there exists an endomorphism on V which is upper triangulable, but its minimal polynomial, let's call that MTX, does not split over F. So this is immediately by our assumption that the claim is false. Okay, fine. So we want to produce a contradiction. That's the goal for this direction of the proof. Fine. So let's say n is the dimension of V, and note that n is at least 2. So why is n at least 2? Because if n were equal to 1, we would have a one-dimensional vector space and an endomorphism over it. So then you can easily show that the minimal polynomial of t splits, because the minimal polynomial of t is going to be a degree 1 polynomial. And that's it. So I leave for you to figure this out, why the dimension is at least 2. Okay, and now since t is upper triangulable, we can find a basis be a basis such that the matrix representation of t with respect to B is upper triangular. Okay, there exists such a basis simply because T is upper triangulable. All right, so let W is equal to span of V1. So therefore, TV1 is equal to lambda 1 V1. Yeah, so maybe before writing this, I should. So say this matrix is. So the entries on the diagonal I will denote by lambda 1, lambda 2 up to lambda n. And there are some, and so all of these entries are 0. You know, when I write a big 0 here, I mean all the entries below the diagonal are 0 because this is an upper triangular matrix. And the other entries I might denote by aij. So, sorry, it's just a notational way of writing. All right, so clearly then TV1 is lambda 1 V1, because what is TV1? TV1, the vector TV1 is lambda 1 V1 plus 0 V2 plus 0 V3 dot dot 0 Vn. So it's nothing but lambda 1 V1. That's how matrices are, the matrix representation of T with respect to a ordered basis is defined that way. So we have that. And therefore, I mean, I'm saying some trivial things. So thus, W is T invariant. So far, nothing anything great has been said. All right. So we have the corresponding, so thus we have an endomorphism T bar on V mod W, which is, well, as usual, defined in this fashion. T bar of V plus W is TV plus W. All right. And here is our claim. So first of all, this is something that I will ask you to justify. So note that V2 plus W up to Vn plus W is a basis for V mod W. So this is an exercise. And this is upper triangular. So the matrix representation, let's call this something. Let's give this a name. This is B bar. So the matrix representation of T bar with respect to B bar is upper triangular. And this is also an exercise. Right, let me just maybe justify it a little bit. Let's calculate. So T bar of V2 plus W, this is equal to what? This is equal to TV2 plus W. What is TV2? TV2 is A1 to V2 plus lambda 2 A1 to V1 plus lambda 2 V2 plus W. Why is that? Because TV2, you look at the second column, and here you have A12. So TV2 is A12 times V1 and A22 times V2, but A22 we have written as lambda 2. So that's why TV2 is equal to this, but this already lies in W, so it gets absorbed, and therefore this is equal to lambda 2 V2 plus W. So this makes sense. I mean, this if indeed this were an upper triangular matrix, then this should have been in the span of V2 plus W, which it is, because this is nothing but lambda 2 of or multiplied by that. All right, now what about T bar V3 plus W? This is equal to TV3 plus W, which is as we did in the previous thing. This is A23 V2 plus lambda 3 V3 plus w. And again, this will get absorbed. So this is equal to v2 plus lambda 3 v3 plus w, which is 823 v2 plus w plus lambda 3 v3 plus w. And yeah, so if you look at the matrix representation, it is indeed upper triangular. I mean, just prove it inductively if you like. Fine. So these two statements I assuming you follow. So therefore, I mean, thus by the previous statement, thus this T bar is upper triangulable, right? And now here is the main point. Since dimension of V mod W is strictly smaller, in fact it is one less than the dimension of V, we must have by minimality of the dimension of V that the minimal polynomial of T bar splits over S. Right, V was a vector space of smallest possible dimension which furnished the counterexample to our claim. Which claim? The claim that upper triangulability implies the splitting of the minimal polynomial. Since we have an upper triangulable endomorphism on a smaller dimension vector space, V mod W, the minimal polynomial of this guy better split. It has to split over the base field. Okay, now finally, what is the minimal polynomial of T? Sorry, what am I saying? So what is the minimal polynomial of restriction of T on W? This is x minus lambda 1. Because maybe I should have written it here itself. So here we have T v1 is equal to lambda 1 v1. So it just immediately implies that the restriction, the minimal polynomial of the restriction of T on W is x minus lambda 1. Because the dimension of W is 1, so you just need to check this to check that the restriction of T when evaluated, when you substitute in place of x, that vanishes. You just need to check it on v1 and it does because of this equation. So yeah, so just agree with this. And now finally, by what we recall, we know that mtx divides the product of empty bar x and empty restriction to wx, W is invariant. So therefore, since this splits, since this is splits and that is splits, this is splits for a very trivial reason because it is already a 1 degree 1 polynomial, and this is splits by our argument earlier. So if something divides a polynomial that splits, this itself splits. So therefore, mtx splits over f. Right? So yeah, I mean, if you want to really justify this last step, why does this split? You use the unique factorization theorem. You can factorize this as product of irreducibles, and then every irreducible will divide this guy. And since degree 1 polynomials are also irreducibles, every irreducible here is dividing a degree 1 polynomial. But if something divides a degree 1 polynomial, the degree of the divider should be at most 1. So that's the implication here, and yeah, that's a basic polynomial thing. So so this direction is proven. This brings us to a contradiction. We had assumed that mtx does not split, but we are proving that it does indeed split, and therefore this direction of the proof, that upper triangulability implies the splitting of the minimal polynomial, is proven. So now we want to do the other direction. So now assume the minimal polynomial splits. Assume mtx splits, and we want to show that T is upper triangulable. So want to show that T is upper triangulable. Okay, suppose not. And as in the previous argument, we may assume that V has smallest possible dimension where one can find an example of such a T. So let me not elaborate on that. And again, so let's say n is the dimension of V. And as usual, or rather as in the previous argument, we have the dimension of P that is 2. Okay, so let's say since the minimal polynomial of T splits, say the minimal polynomial looks like this. Maybe I shouldn't use n because n is used to denote the dimension. So it looks like this, where we are not insisting that these are different or anything. These could all be the same. All right. So since roots of the minimal polynomial are precisely the eigenvalues of the endomorphism, something that I should have recalled in the beginning, but we have proven this. So thus, each lambda I is an eigenvalue of T. So in particular, we can find a non-zero vector such that Tv1 is equal to lambda 1 v1, right? And now let W be the span of v1. Then of course W is T invariant because v1 is an eigenvector. So thus W is T invariant. All right. So we have an operator T bar on V mod W. And we know that the minimal polynomial of T bar, the minimal polynomial of T bar divides the minimal polynomial of T, and thus this splits over F because it's MTX splits over F. Right, this splits over F because it is dividing something that splits over F. So this splits over F, and now by the minimality of the dimension of V, so again by the minimality of the dimension of V, we have T bar is upper triangulable, right? Because its minimal polynomial splits and it is an endomorphism over a vector space of smaller dimension than V. So fine, and now let's say we have a basis which we denote like this, would be a basis of V mod W such that the matrix representation of P bar with respect to B bar is upper triangular. Okay, and here is what I want you to do as an exercise. So show that if B is defined as V1, V2 up to Vn, then B is a basis of V, and the matrix representation of T with respect to B is upper triangular. It's this kind of computation that we did in the previous proof, so I don't want to repeat it. And therefore T is also upper triangulable, which is contrary to what we had assumed. We had assumed that that's not the case. So it's very parallel to the proof in the previous, in the previous direction. So it's no new ideas. All right, now we can read the benefits. So it says something very interesting. Suppose we have an endomorphism on a vector space V, and W is a T invariant subspace. Then T is upper triangulable if and only if the restriction of T on W and the minimal polynomial of the endomorphism induced on the quotient are upper triangulable. Right? This is immediate from the previous proposition simply because of the fact that both of these gentlemen divide the minimal polynomial of T. And so again, this denotes the minimal polynomial of the restriction of T on W, and this denotes the minimal polynomial of T bar. And we have this guy divides the product. So using these two things, we can prove this equivalence. Right? Because if this splits, then both of them split. And if both of them split, then this splits. And splitting is equivalent to upper triangulability, and therefore this is true. So that's very nice. And this in particular, the main theorem in particular implies that every endomorphism on a complex vector space, again everything is finite dimensional, is upper triangulable, because by the fundamental theorem of algebra, every non-constant polynomial splits over the field of complex numbers. So that's very nice. Okay, and here is an example of a non-upper triangulable operator. So we have our favorite 90-degree rotation map, which is defined via this We have seen this many times. The minimal polynomial of this we calculated earlier, and it turned out to be x squared plus 1. And this does not split. Does not split over R, because if it did, then it would have a root in R, but this does not have a real root. And therefore T is not upper triangulable. So that's very nice. No matter what basis you pick, the matrix representation will not be upper triangular matrix. A non-trivial, I would say somewhat non-trivial. It's not obvious that such a basis does not exist, but with our main theorem, it's trivially true. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.